Let us learn about Boolean algebra. Now we know computers use binary logic. In other words, it uses zeros and ones to represent data. In mathematics, there are different branches for different type of questions. You have calculus, you have geometry, and you have algebra. And there's a special category for dealing with Boolean kind of logics. Right? It's known as the Boolean algebra. So the advantage is using Boolean algebra, you can express many things that are represented inside the computer. In addition, we can use Boolean algebra to simplify certain circuits because circuits are basically doing some logical work. And if you can have a mathematical model for it, you will be able to express it, explain it, and also, if possible, to simplify that particular function. First, let us learn about something called a statement. A statement is something that can be either true or false. For example, you can have a statement saying today is Sunday. So it can be either true or it can be either false. You can have mathematical kind of statements as well. Here you can see 1 plus 5 is equal to 10. Now it's a false statement, but still it's a statement. There are things that are not statements at all. You can say, please come here. Now that's not a statement, that's a command. Similarly, you can simply say 1 plus 5. So that's again an operation, right? You need to add the two numbers, but it's not either true or false. You just have to find a result. So there are statements and there are things that are not statements. Now, if a statement can be either true or false, we need a way to represent the two status. So one of the obvious ways to say either true or false, but there are other equal representative as well. You can say high or low. Sometimes you use 1 or 0. In most of the course, in this one, we will be using 1 or 0 because that's how the computers work. So the usual attribution is 1 is true and 0 is false. And if you are using the voltage levels, you can say 5 is the true or the voltage high value and 0 is the low or the false value. There are exceptions to these kind of mappings. For example, you have active low scenarios and you can have different voltage levels. But for throughout this course, we will be sticking to this particular convention. Now, when you have a circuit or system that has multiple logical components, it can be represented using different ways. You can represent a logical circuit using a Boolean expression, or you can use a truth table. We will discuss about truth table from later on time. Or you can have an equivalent logical circuit. Sometimes you can have timing diagrams or even a mathematical model. Here's a very simple example of a truth table. A truth table is basically a table that shows all the possible combinations of the variables. So if it's a circuit, the inputs will be considered as the variables, and so each possible combination of input, you would have a respective output. So the table that's showing that mapping, what is the input combination and what is the respective output combination, output value, will be called the truth table. Now here we have a very simple truth table. We have a statement, X statement. It says today is Sunday. Now since there's only one variable, there's only two possible combinations. X can be either 0 or X can be 1. Now what is meant by X is 0? 0 means false. So X0 means X is false. So X false means X is today is a Sunday. So the false or the opposite of this is today is not a Sunday. The second possible value for the X is 1. So 1 usually represents the true values. So that means X is true. So that means today is Sunday is a true statement. So it must be Sunday. We can expand the number of variables to multiple 1, 2, 3 or many times. So here's another one. So here we have two statements. X statement says today is a Sunday and Y statement says it is raining. So there are two variables. So that means there are 4 possible combinations. in the previous lesson, you learn how to represent numbers. So you can see this is actually binary representation in a given format. So 0, 0 means x is a false and y is a false. X false means today is not a Sunday, and y false means it is not raining. So the meaning of this x0, y0 is today is not a Sunday and it is not raining. You can interpret rest of the table the same way. For example, 1, 0 means x is true. So it is a Sunday, but y is false. So that means it is not raining. So that is a basic idea of how you can represent data or logics in a truth table. Now, here's a small exercise. You can stop the video, pause it, and do this one. Let's say there are 3 machines in a factory, A, B, and C. What are the possible combinations that can have for these machines? You can assume each machine can be individually, independently switched on or off, and draw a truth table for that. Now let's look at the logical operations. Now, having just a truth table or a statement is not sufficient, because you need to connect different statements together. So there are different ways you can connect it. Here we have given 3 of the most commonly used logical operators: the not operator or the conjugation. Sorry, I think this has to be corrected. Not operator is actually the negation. So please correct this particular one. It's a negation. So this is the mathematical expression for that, and this is the Boolean representation. Now in the Boolean expressions, you will see there's a small bar on top of this particular statement. Similarly, you have the AND. In the Boolean expression, you have A dot B, and for the O, you have A plus B. So we will be mainly using these notations for our explanations and rest of the course. And for the time being, remember there's a equivalent logical gate for each of these operators. So this is the NOT gate, AND gate, and the OR gate. So we'll learn a lot about these gates later on, but for the time being, please remember there is a counterpart for each of the Boolean expressions. Now, in mathematics, you have something called precedence. For example, if you have an addition and a multiplication, you should first do the multiplication. And if you have parentheses, you have to do the parentheses first. Similarly, in logical operations, you have a precedence. So the ones with the higher precedence must be completed first. So this is the order of the precedence. So it's important when you are doing a simplification to follow the given precedence. So like in algebra, you have different laws in Boolean algebra. So the laws represented here are quite similar to the ones you find in ordinary algebra. So I will not explain much. You can see if you add y and z first and then add x, it is same as first adding x and y and then adding z. And if you add a 0 to the x, it's same as the x. So these things are quite common. So you can probably get an idea of how they work. So let's do a very small exercise just to warm up ourselves. So the first question that is asked to do is simplify this particular expression. A, B plus C. This is actually for expanding. So you get AB plus AC. That is very straightforward. What about the second one? Now I will give you some time for yourself to try that one. So the second one says A plus B into C plus D. And also try to do the third one. You can pause the video and try to do it. Okay, if you have done that, let's continue the answers. Second one is A plus B into C plus D. So you can basically write A into C plus D plus B into C plus D. So you end up with AC plus AD plus BC plus BD. So that is the one. And last one, the third question, P plus 1 R dot 0. Now P plus 1 simplifies into 1, R dot 0 simplifies into 0, so 1 dot 0 is actually 0. So that means regardless of the values of P and R, this statement will always give a false value. So let's go back to the PowerPoint. There are some laws that are not usually found in ordinary algebra. So these laws are represented here. So if you have x plus x, it doesn't become 2x, it just says x. Because you are adding the logical values, not the numbers. So one statement is true, another statement is true. If you ask any of these statements are true, obviously both of these statements are true. So some of these might feel a little bit counterintuitive. For example, if you look at this one, x into x plus y is simply says x. Is it possible? What happened to the variable y? Now there are two ways you can get an idea what happened to the y. Either you can use the truth table. So you can see if x is 0, this first term becomes 0, so the whole expression becomes 0. So the output x is equal to 0 itself. If x is, if x is 1, this first term we can neglect because you are multiplying by 1. And 1 plus y, again you can neglect the y because it will whole is equal to 1. So output is again equal to 1. So you can use that method, or you can simply do a little bit of calculation to show how it works. So the expression we have is x into x plus y is equal to x. So how can we do it? So if you expand this one, you will get x dot x xy. And x dot x is actually x, and this is xy. Now you can take the common term out. You can take the x out. So you have 1 plus y. Now we know 1 plus y. So let me write it here. We have the x 1 plus y. Now 1 plus y is 1. So we have x dot 1, which is x. So our original law is correct. You can say left hand side is equal to right hand side. Right. Now let's look at several more examples of these laws. You have the absorption laws and you have the complements. And there are two very important laws at the bottom. They are called the De Morgan's law. These are very important when you want to expand a certain expressions. You can say x plus y and the whole thing inverted or the whole thing bar is equal to x dot bar, x bar dot y bar. Similarly, you can see x dot y whole thing bar is equal to x bar plus y bar. So that is De Morgan's law. That is again a very important law. So let's do another example. So I will give you some time, pause this video and try to do it yourself. It should give you some idea of how you can apply these given laws. Okay, I think you have tried the examples. Let's try the question. So let me start with our first question. Our first question is a into a bar plus b. So this is very straightforward. So a dot a bar plus b, a times b, let's put it here. So a dot a bar is 0. So 0 plus ab is equal to ab. So that is quite easy. What about the second one? Second question says af and then you have G plus C bar plus G bar C bar F. Now you can see there is a parenthesis, but you have a total negation at the top. You have a bar. So we have to use De Morgan's law if you want to simplify this part. So you can say F. Instead of this, I can say G bar dot C bar using De Morgan's law plus G bar C bar F. You can say De Morgan's law. There are some common terms here. So you can take this common term G bar, C bar, F bar. So you will end up with A plus 1. This become 1. Therefore, the answer becomes G bar, C bar, F bar. What about the third one? Now, if you try to go there directly and try to simplify it, you will find it quite hard. But take a closer look at what this expression has. Now, if you look carefully, you will notice there's something called AB plus AB whole thing bar. So what is this? So if you take this as term x, this would be like x bar. So when you add these two terms, you should end up with a 1. Right? So if you end up with a 1, you can see 1 plus something, and plus another term. So it doesn't matter how many terms you add to the 1, your result would be 1. So when you simplify, you only need to say, you can say AB plus AB bar is equal to 1, and then 1 plus all these things is equal to 1. So you don't need to go through all the length. You can very simply say this whole expression is equal to 1. So I hope you have got idea about what the Boolean algebra is about and how you can use it. Please try the exercise on the related past papers. There are many questions. And if you have any questions, you can ask them during the lectures or the Zoom lectures we have. By the way, I forgot one important rule. That is the duality. So in simple terms, what duality means is, if you have some law, there is a counterpart or the duality of that particular law. Only thing you need to do is, you have to replace the O operator with AND operators with O operators, and invert or put a bar for all the values. Right? Then you get another law that is equal to the first one, that will be always valid. Right? So you might see some examples in here as well. Okay, it's not there, but that's basically the duality. And try the examples, and we will see you on the next Zoom lecture.